Hey guys, welcome back to another RASK Maths video, and in this video I'm going to be showing you guys a really simple visual proof of Pythagoras' theorem. Now, if you somehow don't know what Pythagoras' theorem is, it basically states that in a right angled triangle with sides A, B and C, where A and B are the two perpendicular sides and C is the hypotenuse, A squared plus B squared is equal to C squared. And what this is actually saying is that the square of this side plus the square of this side is going to be equal to the square of this side. Or another way of looking at it is C is equal to the square root of A squared plus B squared. Square root is a one-to-one function for positive numbers, which is what we're interested in as lengths. So therefore, when you're given two lengths of a right angled triangle, there's always going to be only one solution for this third length, which I guess is a special case of the right-hand side congruency law, which is not true if this angle isn't 90. Okay, so how can we prove it? Well, this is a really simple visual proof and it's been used a lot. In the future, I'll think of a more interesting one or more sort of, original one. But here's a basic proof. So we construct a square and let's imagine we have four of these triangles and we just arrange these triangles so we have four of these triangles, and what we want to do is just put these triangles in the square such that we get sort of this pattern. So obviously, since they're all identical, it's all going to match up in the end, but my drawing might not. So let's just imagine all of these squares are identical. I mean, not all these squares, all these triangles are identical. Alright, so here are our four triangles. There's one, there's two, there's three, and there's four. Now, the main thing to note is that this length is going to be A. We're going to call A the short side without loss of generality. And this side is B. And since all these triangles are identical, this is true for all of the sides of a square, which I guess is why it's a square. So what this tells us is that the side lengths of this square are A plus B. So therefore, the area of the square is going to be A plus B multiplied by A plus B, or A plus B squared. So there's the area of the square, but we want to find another way of representing the area of a square. And what is that other way, you might ask? Well, you can notice that we can do some angle things. So we know that this is theta. We know that's 90. If we say this angle is theta, this is going to be 90 minus theta. By congruency, this angle is also going to be theta. So since these have to sum to 180, this basically tells us that this angle has to be 90. That's how we can deduce that it is, in fact, a square on the inside. And should be fairly obvious from congruency. But then what we can use from that information is the fact that the inside has also formed another square of side lengths C, right? Because we constructed this by just, this side length is really just a side of this triangle, C. And we can also count up the area of these four individual triangles. So the area of one triangle, I'll just say this is AT, and that's equal to, well, we know the area of a triangle is just half base times height. So in our case, the base is going to be B, and the height is going to be A. So we can write the area of one triangle is just 1/2 AB. And we know the area of this inside square is just going to be C squared. Fairly obviously, because it has side length C. So we need to find an expression to link all of these quantities. And what do you notice? Well, the area of this square plus the area of 4 of these triangles adds up to the area of the bigger square. So we can write this as area of square is equal to area of the inside square plus 4 times the area of a triangle. And this is the key relationship which we need to prove Pythagoras. Since now we've got all of these quantities in terms of a and b, we can just substitute them in and we should be able to derive Pythagoras' theorem. So a plus b squared is equal to c squared plus 4 times this, so that's just going to be 2ab. Expanding out this bracket, we get a squared plus 2ab plus b squared is equal to c squared plus 2ab. Now clearly the 2ab's cancel out, so that leaves us with a squared plus b squared is equal to c squared. A nice and easy proof. And yeah, that was proven a 2000-year-old Pythagorean theorem. So thanks for watching, and that was a simple proof of Pythagoras' theorem. See you guys in a future tutorial. Bye.